Okay guys, now we are ready to talk about equilibrium for a rigid body. Now the last chapter, chapter 4, is everything we'll discuss. Getting ready for chapter 5. Okay, talk about moments, right, and couple moments, okay, and all the equations for it and simplifications of the moment force system and all that. Now all that are preparing yourself for this chapter. Okay, and since we've done all the preparations, chapter 4, and also chapter 3, and also chapter 2 actually, this chapter is actually quite short, okay, because the equations is really nothing new, okay. All we're doing here in this chapter is just put everything together and analyze a rigid body, okay. So, this is a really important chapter, but everything we've done so far, okay, are equally important, okay. Okay, now recall what we've done before. Chapter 3, equilibrium for a particle. Right? Particle only has one equation, okay, for equilibrium condition. That is, sum of forces equals 0. Now this is a vector equation, right? So depending on whether you're dealing with 2D or 3D, you have a number of equations, scale equations to work in, right? X, Y, or Z, right? So 3D. Okay. So now we're dealing with rigid bodies. Okay, now once again, the major difference between a rigid body and a particle is that in rigid body we consider now the rotational effect, right, or the tendency to want to rotate. Okay, even though the actual rigid body may not be rotating, let's say a calculator, right? So a calculator can be considered as a particle if the rotation doesn't matter at all. Okay, we don't care about the rotational effect. But as a rigid body, now we need to be considering the tendency to want to rotate. Let's say if I pivot it at this point, right, or at this left-hand side, okay, this is glued to a wall or something, okay. So if I apply a force down here, right, so the tendency, right, for this rigid body to want to rotate must be taken into consideration, okay, if you consider this as a rigid body. So now as a rigid body, other than this sum of forces equation, we must consider the second equation, which is sum of all moment about any point O, okay, and this point O can be anywhere on the rigid body or outside the rigid body. It doesn't matter. Okay? As long as you sum this moment about some point. Okay? And they all go to 0. Okay? So these two equations together give you the equilibrium condition for a rigid body. Okay? So this sum of forces equation, it's pretty straightforward, just like before. Okay, just a particle. Alright? So you sum all the forces up, right, in each direction, right, and set them equals 0, and that's it. Now this sum of moment, okay, is also a vector equation. Okay, moment is a vector, right? It has direction. The sum of moment, this moment includes the moment created by each of the forces. Okay, that is R cross F term, as well as any applied moment, applied couple moment. Okay, so that's where we bring in chapter 4, right? All the couple moment stuff, right? So everything, all the moments, okay, must equal to 0, right? So they cancel out each other. So these two are your equations, right, for the whole analysis for rigid body. Okay, it's really, really simple. Two equations governs everything. Okay, but realize that these two are vector equations. Okay, dealing with vectors now. Okay, so let's consider maybe the most simple case, right? 2D, right? In 2D space, these two equations will reduce to these. The sum of forces equation will have x and y components. Okay, so each equation now is the scalar equation, right? So now you can plug in numbers, right? And then the sum of moment equation, now it's a scalar also, the sum of moment about any point. Okay, any, I just call it A, right? Point A for any point, right? Again, this point can be on the body or outside the body, doesn't matter. Okay, so now you're dealing with scalar equations, right? So these comes from these original general equations, right? For 2D case. So let's say I have a rigid body, okay, any size, any shape, right? On XY plane, okay, X and Y defined this way, okay? So this rigid body is subject to, let's say, 4 forces, okay? F1, 2, 3, and 4. Also, it's subject to 2 couple moments, okay? Applied moment, right? So these 2 and one of them 2 are couple moments, right? So they are externally applied, okay? As if just recall, like, opening a vault, a door or steering wheel, right? So the forces that you apply, okay, are actually couple moments, okay? So you actually apply a couple moments. So those are applied, externally applied. So all these, okay, you draw the forces as well as the applied couple moments on this free body diagram, okay? So now back in chapter 4, we talked about all the the forces and all the couple moments and how to reduce them and all that. Now there's one more category of forces and moments, okay, when you talk about before we can actually start analyzing equilibrium for rigid body. That is reactions. Okay. So for any rigid body, there has to be some kind of reaction because you have to have some kind of support. Okay. So this means that, let's say I have a rigid body, right? This Sharpie right here. Okay. It's resting on a surface. So at this surface right here, the contact surface, that's where the support takes place. Okay? And even if, let's say I'm holding this Sharpie right here, the point of contact is where the support takes place. Right? And for any rigid body, there has to be some kind of support. Okay? Let's say a bridge. Right? A bridge is sitting on typically two platforms. Okay? Let's say the edge of a cliff. Right? So at those points, those support points, they are actually supports. And whenever you have support, you always have reactions. Okay? So different kinds of support will have different kinds of reactions. So if you look at page 202 or 203, it's the whole list of different kinds of support and different reactions. Okay? And the most common ones that you might encounter would be something like, let's say you have a rigid body, that's just a metal bar. Okay? And one side of it is resting on one point. Okay? Let's say something like this. Okay? So it's resting on it. It's just nothing is constraining it. Right? So it's just sitting on it. Okay? And then let's say on this other end, it's pivoted. Okay? So it's free to rotate. Okay? So it can go up and down like this. Okay? So well, let's consider this first, right? It's simpler. So this, it's just simply resting on a point, one single point contact. So the reaction at this point, while this rigid body is in contact with this support right here, so the only reaction is straight up. Okay? So that's your reaction. Okay, reaction. Right? There's no horizontal reaction. Okay, because there's nothing that's resisting, okay, the motion, of this rigid body. Okay, so you can think of reaction forces as any kind of resistance. Okay, resistance to the motion or to the potential motion of the rigid body. Okay, so now this pivot right here. Okay, so this rigid body is free to rotate like this, right? So at this pivot point, okay, let's look at the resistance. Okay, think about it. Okay, we're resisting, we're constraining the motion of this rigid body at this point, okay, in both x and y direction. So therefore, in each direction, you have a reaction force. Okay, call it Rx. Reaction Ry. Okay, because we're constraining this point in either x or y direction. So this point right here cannot move, cannot displace or translate in x or y direction. Right? It's fixed there. But it's free to rotate. Okay? What if say I have this same rigid body right here, instead of pivoting it, now I don't allow this to rotate at all. That is, maybe I glue it to a wall. Okay? In that case, this is the only point where support is located, right? So, what about the reaction? Let's say, at this point right here, I don't allow this point to move to the right or left or up or down, right? So therefore, I have reaction force, also Rx, right? And then Ry, same thing. I run out of space, so I can just draw this down here. Right? So reaction force X, reaction force Y. Okay? Where I'm constraining it. Right? So this rigid body is resisting the constraint. Okay? By having these two reaction forces. But also at the same time, since I'm not allowing this rigid body to rotate, like this case out here, right? So think about the rotational motion, rotational resistance. So at this point, this rigid body will also have a counter moment, right? To take into account the resistance to want to rotate, okay? Because I don't allow this rigid body to rotate. So the resistance to rotate simply in the form of moment. Let's say this is point A, right? So okay, so these three are the reaction. Okay, these are the reaction forces. This is the reaction moment. Okay, so all these. Okay, now let me use blue for this moment. Okay, just to be consistent with this picture down here. So all these reactions must also appear in this free body diagram for your rigid body. Okay, so all these forces include reaction forces as well as any applied force, external forces. Let's say if you push the rigid body, right? So this is applied, externally applied forces. The mass of this rigid body will also be considered external effect. So the mass will have a weight, right? So the weight is considered external force, right? And friction, for example, okay, so it's considered contact force, okay? So any external force, as well as applied moment, okay? For example, couple moment, right? Okay? Or reaction moment. So with all these in place, now here are the solution steps. Okay, it's very, very logical. It's identical to how you solve for particles back in chapter 3. You define a coordinate system first, and then you draw a free body diagram. Right? So just the rigid body without any attachments, okay, freed up, and then draw the forces and apply couple moments, including reaction. Solve for it, and you bring in geometry, and say trigonometry, okay, if necessary, and that's it. Next we'll look at an example.